For generations, humanity has gazed up at a distant red dot in the night sky and dreamed of setting foot on it. That destination is Mars, the elusive next frontier. But the question that has haunted explorers and scientists alike is not just how to build a rocket big enough to get there. It's how to solve an intricate web of challenges that stand between Earth and that dusty, mysterious world. These hurdles span engineering feats, biological risks, and the unforgiving realities of space travel. This is the untold story behind the question: how will humans actually make it to Mars? Right now, Mars sits roughly 140 million miles from Earth on average. But that distance isn't constant. Both planets orbit the Sun at different speeds and distances, so the gap between them varies wildly, from as close as 34 million miles to as far as 250 million miles. This variation creates a fundamental barrier: timing. The planets align in a way that makes travel to Mars feasible only about once every 26 months. Launch during these windows, and the journey becomes shorter and more fuel efficient. Miss it, and the wait is another 2 years. Even with perfect timing, the trip is long. Estimates put the one-way voyage at about 6 to 7 months, around 180 to 210 days, in the vast emptiness of deep space. That means 6 months beyond Earth's protective magnetic shield, exposed to cosmic radiation and dangerous solar particles. It's 6 months in near-zero gravity, where astronauts' bones weaken and muscles waste away. It's 6 months confined in a tight spacecraft with the same small group of people, cut off from life on Earth. And that's just the outbound leg. A Mars mission unfolds in 3 daunting phases: the journey there, time spent on the Martian surface, and the return trip home. The surface stay can't be brief. The orbital mechanics of the planets make an immediate turnaround impossible. Instead, astronauts must wait for the next favorable launch window, about 500 to 600 days later, or roughly a year and a half stranded on Mars. Adding it all up, a round-trip mission stretches to around 900 days, nearly 2.5 years away from Earth. So how can humans survive and function for that long in such extreme conditions? The first step is simply leaving Earth, which means building a rocket powerful enough to escape our planet's gravity. And Earth's gravity is no joke. Launching anything into space demands huge amounts of energy. The math of rocketry is brutal. To send 1 pound of payload, you need many pounds of fuel. But fuel itself has weight, which requires even more fuel to lift it, creating a snowball effect that quickly escalates the total mass needed. Current projections say a Mars mission will require a launch vehicle capable of delivering between 50 and 100 metric tons to Mars, depending on the mission plan. That's far beyond the capacity of any rocket flying today. Enter SpaceX's Starship, a 2-stage, fully reusable rocket system designed specifically for missions beyond Earth orbit. Standing roughly 121 meters tall, taller than a football field is long, and weighing about 5,300 metric tons when fueled, Starship consists of a super-heavy booster with 33 powerful Raptor engines burning liquid methane and oxygen, stacked beneath the Starship spacecraft itself, which carries 6 additional Raptors optimized for different phases of the journey. The super-heavy booster's combined thrust exceeds 73.5 meganewtons, more than double the power of the Saturn V rocket that sent astronauts to the Moon. Starship's baseline reusable form can haul between 100 and 150 metric tons into low Earth orbit, enough to support a Mars mission, but only if the mission is designed carefully. Here's the catch: even when fully fueled, a single Starship can't carry enough propellant to get from Earth orbit all the way to Mars. The spacecraft needs to accelerate out of Earth orbit, cruise millions of miles through space, and then slow down to enter Martian orbit or land safely. This requires a huge change in velocity, known in aerospace engineering as delta V. A single tanker just can't hold all the fuel required while also carrying crew and supplies. SpaceX's answer is orbital refueling. The plan? Launch the crewed Starship into low Earth orbit with mostly empty tanks. Then send up multiple tanker Starships, stripped down to carry mostly fuel, no crew. Each tanker docks with the cruise ship, transferring propellant bit by bit. Depending on the mission and payload, This process could take between 8 and 16 tanker flights to fully fuel the crew vehicle. Once topped off, the Starship can make the leap to Mars. This approach, multiple launches supporting one mission, is a radical departure from traditional space exploration. It's complicated, demanding a tight schedule of flawless launches, precise orbital maneuvers, and complex docking operations. But it's the only practical way to get enough fuel to Mars without building an impossibly huge rocket. The next hurdle: proving this refueling technique works. Refueling spacecraft in orbit has never been done before, especially not at this scale. SpaceX is actively developing the necessary technology, with demonstration missions planned, but until it's tested successfully in space, the concept remains theoretical. Once Starship leaves Earth orbit, it enters the harsh frontier of deep space, an unforgiving environment rife with radiation hazards. Outside Earth's magnetic shield, astronauts face two main radiation threats: galactic cosmic rays and solar particle events. Galactic cosmic rays are ultra-high-energy particles originating from beyond our solar system, mainly protons, but also heavy ions like iron and carbon, traveling near the speed of light. These particles can penetrate human tissue and spacecraft materials, delivering dangerous doses of radiation. For a full Mars mission lasting around 3 years, astronauts are expected to receive nearly 900 millisieverts of radiation exposure, about 300 times the average annual dose on Earth. Such levels significantly increase risks of cancer, cardiovascular disease, cataracts, and cognitive decline. Animal studies show high-energy radiation damages brain cells, reducing neural connections and impairing memory and decision-making. Some scientists estimate that 1 in 5 astronauts on a long Mars mission could suffer noticeable cognitive decline. Solar particle events are bursts of lower-energy protons ejected from the Sun during solar flares or coronal mass ejections. These events can deliver lethal doses of radiation in just hours if astronauts are unprotected. The upside is that solar particle events are somewhat predictable, especially during periods of heightened solar activity, giving crews some warning. The downside: warning means nothing without adequate shielding. Traditional radiation shields like lead or aluminum are heavy and less effective against these high-energy particles. Worse, when cosmic rays hit heavy materials, they can create dangerous secondary radiation. That's why current research focuses on lightweight materials rich in hydrogen, like water, polyethylene, or advanced substances such as hydrogenated boron nitride nanotubes, that better absorb radiation without producing harmful byproducts. Starship's design includes some radiation shielding, but whether it's enough for a Mars mission is uncertain. Additional protection might be needed, which would add mass to the spacecraft. Alternatively, supplies like water, food, and equipment could be arranged around crew quarters to create a makeshift radiation shelter. Still, even the best shielding can't eliminate exposure entirely. NASA's current astronaut career radiation limits allow for roughly a 3% increase in lifetime cancer risk. A Mars mission would exceed that threshold, raising tough questions about acceptable risk levels. Arriving on Mars doesn't end the challenges. Landing on the red planet is a feat of its own. Mars' atmosphere is a tricky hurdle, thick enough to cause heating and drag during entry, but too thin to slow down a heavy spacecraft as effectively as Earth's atmosphere does. Earth's dense atmosphere lets parachutes work wonders, slowing spacecraft gently to the surface. Mars' atmosphere, with less than 1% of Earth's density, can't do that alone. Past Mars landers and rovers have relied on a mix of heat shields, parachutes, and retro rockets to land safely, but those vehicles weighed only about 1 metric ton. Starship, by contrast, weighs around 100 metric tons empty, and far more when loaded with crew and cargo, about 100 times heavier than anything landed before. Aerodynamic drag isn't enough to slow Starship. Instead, it must use its engines to decelerate during descent, a technique called supersonic retropropulsion. The spacecraft fires its engines while still traveling faster than the speed of sound, pushing against its forward motion to slow down. Until recently, engineers weren't sure supersonic retropropulsion would work. Firing engines backward at high speed through an atmosphere creates shock waves that could destabilize or damage the vehicle. But SpaceX has been testing this method with Falcon 9 boosters returning to Earth, successfully managing shock waves and showing they form a protective bubble around the rocket, reducing heating and buffeting. This gives hope that supersonic retropropulsion can work on Mars, though challenges remain. Mars has unpredictable winds and frequent dust storms. Landing precision is critical. The spacecraft needs a relatively flat landing zone free of large rocks or slopes to avoid tipping over. Current technology can land within about a 20-kilometer ellipse, good, but not precise enough for a mission where every meter counts. To improve accuracy, new navigation systems like terrain relative navigation are in development. These use onboard cameras and sensors to recognize landmarks during descent and adjust the trajectory in real time, aiming to land within a few hundred meters of a target. Even with perfect navigation, landing remains risky. Engine firing must be timed exactly right, too soon, and fuel runs out before touchdown, leading to a crash. Too late, and the vehicle impacts the ground hard. The margin for error is razor thin. Once on the surface, astronauts face a harsh world. Mars is cold. Surface temperatures swing from about -125 degrees Celsius at the poles in winter to a balmy 20 degrees Celsius near the equator in summer, averaging around -60 degrees Celsius. The atmosphere is mostly carbon dioxide, with traces of nitrogen and argon, but no oxygen. Air pressure is less than 1% of Earth's. Any human exposed directly to the Martian environment would lose consciousness within 15 seconds and die within a minute and a half. That means a pressurized habitat is essential for survival. Early mission designs involve sending a habitat module ahead of the crew, which can deploy automatically, inflating or unfolding into a livable space. This habitat must provide breathable air, drinkable water, food, temperature control, radiation shielding, and waste management, all in a reliable system with no possibility of emergency rescue or resupply. If something breaks, the crew must fix it themselves, a daunting responsibility. One strategy to reduce risk is to use Mars' own resources, a concept called in situ resource utilization, or ISRU. Mars offers resources that can be harvested and processed to support astronauts. The carbon dioxide atmosphere can be converted into oxygen for breathing and methane for fuel. Water ice, buried beneath the surface in many places, can be extracted, melted, purified, and used for drinking, hygiene, and growing food. The soil contains minerals that might be used for construction or manufacturing. But extracting these resources requires heavy equipment, drills, excavators, chemical plants, power systems, all designed, tested, and transported to Mars, and all needing to operate reliably in an environment with extreme temperature swings, frequent dust storms, and zero external help. NASA is actively developing ISRU technologies. In 2021, a small experiment called MOXIE was sent to Mars aboard the Perseverance rover. MOXIE successfully produced oxygen from the Martian atmosphere multiple times, proving the concept works on a small scale. Scaling this up to support a crew and fuel a return rocket, however, is a massive challenge. A full-scale system would need to produce about 25 tons of oxygen over a year and a half, demanding enormous power and robust machinery. At the heart of the mission lies the critical question: how do astronauts get home? Carrying all the return fuel from Earth isn't practical. The mass requirements would be astronomical. Instead, fuel must be produced on Mars before the crew can launch back to Earth. This means ISRU systems must be not only functional but dependable, or the crew could be stranded on the red planet, millions of miles from home. To make a crewed mission to Mars a reality, one of the biggest challenges is producing rocket fuel directly on the planet. Carrying all the propellant from Earth simply isn't practical. It would be prohibitively heavy and expensive. So, the plan relies on turning Martian resources into usable fuel right on site. The most widely accepted method involves creating methane and oxygen from the carbon dioxide-rich atmosphere of Mars. Here's how it works. First, carbon dioxide is harvested from the thin Martian air. Then, It's combined with hydrogen in a chemical reaction known as the Sabatier process. This reaction produces methane, which can be used as rocket fuel, and water as a byproduct. The water is then split through electrolysis into oxygen and hydrogen. The hydrogen feeds back into the Sabatier reactor to keep the cycle going, while the oxygen is stored as an oxidizer for the rocket. Both methane and oxygen are kept in cryogenic tanks, ready to power a Mars ascent vehicle for the journey home. If astronauts can access local water, maybe from underground ice, the process becomes even more straightforward. They can directly electrolyze that water to generate the hydrogen and oxygen needed for the Sabatier reaction and fuel storage. But setting this up isn't simple. It demands a suite of heavy-duty equipment, chemical reactors, electrolyzers, compressors, and insulated storage tanks. All of it requires a huge amount of energy to run continuously for months, maybe even over a period of about 500 days. Estimates suggest the power plant must generate several hundred kilowatts nonstop, which is more than any spacecraft has ever managed before. So, what kind of power sources could provide such a massive, reliable energy supply on Mars? Two leading contenders are solar panels and nuclear reactors. Solar power is attractive because it's a proven, well-understood technology. Photovoltaic panels are lightweight, have few moving parts, and don't involve complex machinery. But Mars receives less sunlight than Earth because it's farther from the sun, so solar panels produce less power. They're also vulnerable to dust accumulation. Those infamous red dust storms can coat the panels and drastically reduce their output. Analyses indicate that near the Martian equator, solar power might be workable, especially if paired with hydrogen fuel cells to provide electricity during the long, cold nights. However, at higher latitudes, where sunlight is weaker and dust storms are more frequent, nuclear power becomes a more dependable choice. NASA has been developing compact nuclear reactors called kilopower units. These small nuclear systems use uranium fission to generate heat, which is then converted into electricity. Each kilopower unit can produce about 10 kilowatts continuously, day and night, regardless of weather. For a Mars mission's energy needs, multiple units could be linked together to provide the necessary power output. But there's a catch. Nuclear reactors are heavy, and they require significant shielding to protect the crew from radiation. This adds even more mass. Still, their reliability on Mars is a huge advantage. When lives depend on continuous power, consistent performance trumps efficiency. Power isn't the only resource that astronauts will need in abundance. Food is another critical factor. An adult human needs roughly 2,000 to 2,500 calories every day, depending on their activity level. Over a mission lasting about 900 days, that adds up to nearly 2 million calories per crew member. Bringing all that food from Earth is possible but not ideal. Prepackaged meals consume a lot of space and weight, and after spending a year or more in a confined environment, the crew will crave fresh, varied nutrition. That's why scientists are developing bioregenerative life support systems, essentially, growing food on Mars. The idea is to cultivate crops in pressurized greenhouses that recycle carbon dioxide and produce oxygen, helping maintain the habitat's atmosphere. Fresh plants can boost morale and provide essential nutrients. Experiments aboard the International Space Station have already shown that plants like lettuce, radishes, and tomatoes can grow in microgravity. Since Mars has about 38% of Earth's gravity, growing plants there should be easier than in orbit. However, Martian soil isn't naturally ready for farming. It contains perchlorates, poisonous chemicals that must be removed before planting. Plus, the soil lacks organic matter and helpful microbes that Earth plants rely on. To solve this, astronauts might need to bring soil from Earth or develop ways to process the native Martian soil to make it safe and fertile. There's also the issue of light. Mars receives less sunlight, and dust storms can block what little there is. Supplemental lighting inside the greenhouse will be necessary, especially during the long winters or extended dusty periods. Lastly, growing food requires a lot of water, so efficient recycling systems will be needed to capture moisture from the air and waste, then reuse it for irrigation. But beyond fuel, power, and food, the biggest hurdle might be something less tangible: the human mind. The psychological toll of a Mars mission could be the greatest threat to success. Crews will be confined together in tight quarters for months, isolated millions of miles from Earth, with no chance for a quick escape. They'll face loneliness, monotony, stress, and the constant pressure of living in a hazardous environment. Privacy will be scarce, and interpersonal conflicts are almost inevitable. Unlike on Earth, there won't be therapists to call or a simple break from the group when tensions rise. The crew will have to manage conflicts and emotional struggles on their own. Studies of astronauts on the International Space Station and volunteers in isolation experiments on Earth have highlighted key psychological risks. Depression is common, with feelings of sadness, fatigue, and low motivation. Sleep disturbances also occur. Small annoyances can quickly escalate into serious conflicts when there's no way to avoid others. Stress, radiation exposure, and lack of sleep can lead to cognitive decline, affecting memory, attention, and decision-making. NASA has developed support systems to lessen these risks. Crews receive training in stress management and conflict resolution. They have scheduled private counseling sessions via communication with Earth. They get care packages and surprise messages from loved ones to boost morale. But communication delays between Earth and Mars seriously complicate this. Radio signals take anywhere from 4 to 24 minutes each way, depending on the planet's positions. Real-time conversations are impossible. If someone is struggling emotionally, they can't just pick up a phone and get immediate support. They'll have to send a message and wait, often half an hour or more, for a reply. This delay deepens the sense of isolation. To address this, researchers are developing onboard psychological tools. One is a computer-based therapy program that guides astronauts through exercises to manage problems and improve mental health. Another is a cognitive self-assessment tool, allowing crew members to regularly check their mental state, similar to how one might monitor blood pressure. Ultimately, the mission's success relies on the people chosen to go. Selecting individuals who are resilient, adaptable, and compatible with each other is critical. The human factor may be the most unpredictable variable of all. When might all this become reality? Elon Musk, founder of SpaceX, has suggested the first uncrewed Starship mission to Mars could launch as soon as the year 2026 during the next optimal launch window. That initial mission would focus on landing safely, testing systems, and proving that the technology works on the Martian surface. If successful, the following window in 2028 might see additional cargo missions bringing supplies and infrastructure. Then, maybe in 2030 or 2032, the first crewed mission could take off. These timelines are ambitious, some say unrealistically so. Developing, testing, and certifying every piece of technology will take time. Delays are almost guaranteed. But even if the schedule slips by a decade or more, sending humans to Mars within the next 20 years remains an extraordinary goal. Here's what's clear: going to Mars is within reach. The rockets exist and are flying. Orbital mechanics have been mastered. Dozens of robotic missions have paved the way. We know how to land safely using supersonic retropropulsion, a technique proven but still under refinement. Producing oxygen and methane on Mars has been demonstrated by experiments like MOXIE on the Perseverance rover. Scaling these processes is a challenge of engineering, not science. Radiation protection is improving with better shielding materials and medical countermeasures. Growing food in space has been proven on the ISS. What remains uncertain is whether all these pieces can be woven together into a reliable, safe, and integrated system. That's the final frontier of preparation. Exploration means embracing the unknown. The first crew to Mars will face dangers we can predict, and those we cannot. They will be utterly alone, millions of miles from home, in a world that has never supported human life. If something goes wrong, there will be no rescue mission arriving in days or weeks. They will have to rely on their training, ingenuity, and each other to survive. It's a daunting prospect, but also humanity's boldest endeavor. Just 100 years ago, the idea of flying to the moon was pure science fiction. 50 years ago, we made it happen. Now, Mars is no longer a distant dream. It's a destination. Looking up at the red dot in the night sky, one can't help but feel a profound connection. Mars has captivated human imagination for millennia. Ancient cultures tracked its movements, weaving myths and stories around it. Now we know it's a world with the potential to become home. The first explorers will endure hardships unimaginable to most, but they will also witness wonders no one else has seen. They'll watch Earth shrink into a tiny blue speck as Mars grows larger day by day. They'll descend through the thin, dusty atmosphere and set foot on alien soil for the very first time. And while they will be the pioneers, they won't be the last. A successful mission could open the floodgates, building habitats, expanding infrastructure, and maybe even turning Mars into a second home for humanity. Or perhaps not. The unknowns are many, but the choice is ours. Because staying confined to a single planet forever is not in our nature. Humanity has always been driven to explore, to push boundaries, to reach for the stars. Mars is calling.